Okay, I think we are ready to go. Thank you everyone for joining today. One more lecture of our PIM course. Today we are going to continue talking about the UPMEM PIM architecture, the first commercially available PIM architecture, and in particular we are going to talk about the microbenchmarking study that we did with this architecture in order to figure out the internal characteristics of the architecture. Whenever you want to ask any question, please don't hesitate to stop me, and I will also keep an eye on the YouTube chat in case that there are any questions there. So remember, this slide is a let's say flagship slide for the UPMEM PIM architecture, where we can see some DIMMs, and these DIMMs contain several chips. 8 or 16 chips typically, and inside the chips we have memory arrays, DRAM memory arrays, and we also have small processors called DRAM processing units, or DPUs. If we take a closer look at the system, we identify the UPMEM DIMMs that coexist with main memory DIMMs, conventional DRAM typically, and in each of the DIMMs we have, as I said before, 8 or 16 chips, and these represent 1 or 2 ranks of 8 chips each. What is what we have inside each PIM chip? There are 8 DRAM banks called MRAM of size 64 megabytes in the current generation of this architecture. And then there are 8 DRAM processing units, or DPUs. Each DPU can access 1 MRAM bank. If we take a closer look at the internals of the DRAM or the PIM chip, we find the control and status interface for the CPU to communicate with the pipeline of the DPU. We also have a DDR4 interface for the CPU to access the DRAM banks. Then here we have the 8 DRAM banks and the corresponding DMA engines to access them. And the way we access them is by either moving instructions from the MRAM to the IRAM, or moving operands back and forth between the MRAM and the WRAM, which is a scratchpad or software managed cache. And remember as well that we have a pipeline, and this pipeline has 14 stages. The current generation, or let's say the most powerful version of the UPMEM PIM system right now, has DPUs that can run at frequency of 425 megahertz. For the experiments that I'm going to show here, the experimental results that I'm going to show in this lecture, we used a system that can run at a frequency of 350 megahertz. The pipeline, as you may remember, is fine-grained multi-threaded. It can hold up to 24 hardware threads, and in total it has this pipeline 14 pipeline stages that you can see on the slide. The ISA, the instruction set architecture of this UPMEM PIM architecture, is a specific 32-bit ISA. It also allows compilation of 64-bit code, and the compiler is LLVM based. Okay, so now we are going to start understanding even more about these DPUs and about this PIM architecture. And the way to do this is to do some microbenchmarking. The idea of microbenchmarking in general is like using very simple programs that can somehow help us characterize what are the inherent characteristics of this architecture. And in the end, what we are going to do here is measuring these basic characteristics, such as the arithmetic throughput or the bandwidth to the 2 main memory spaces that we can use for data and for operands. So we are going to start exactly with the arithmetic throughput that the DPU pipeline can achieve. In the figure, you also see the WRAM, because the WRAM is the place where we store the operands, input and output operands. So every time that we perform an operation, we will read data from WRAM, and we will write results to WRAM. Let's take a look at that microbenchmark that we prepare to measure the arithmetic throughput. The goal, as we already said, is to measure the maximum arithmetic throughput for different data types and operations. And to do so, what we do is creating this microbenchmark. In this microbenchmark, you're going to see it in the next slide. In this microbenchmark, what we essentially do is going over one array in WRAM and performing operations on the elements of this array. In particular, we perform a read, modify, write operation on each element of the array. We run our experiments on a single DPU, and we vary the number of tasklets from 1 to 24. And we use different arithmetic operations, addition, subtraction, multiplication, and division, and for different data types, integers of 32 bits or 64 bits, and then floating point, either single precision and double precision. To perform our measurements, we use an accurate cycle counter that the SDK provides. And in our measurements, we include the accesses to WRAM, as I said before, not only the arithmetic operation, let's say the addition, where the operands are already stored in a register, because these operands, these input operands, are going to come from WRAM. We are including the accesses to WRAM in our measurements. So let's take a look at the this example microbenchmark. In particular, this one is for addition of 32-bit integers. And as you can see, in the top of the slide, you see the C-base code. This is what we write, is a high-level language code that we write. As you can see, it's pretty simple. In the bottom part of the slide, what we see is the compiled code in the DPU ISA. As I said, the code is very simple. You see that the only thing that we are doing here is going over one array of a certain size. We go over all elements of the array, read these elements, perform some operation, in this case, an addition, and then we store the result back in the same position. This array called buffer A in this particular slide, it's allocated in WRAM, and the way of allocating memory space in WRAM is by using this memalloc, as you see. So if we take a look at how this the compiler compiles this C-base code into the DPU ISA, here we can identify the for loop, and this for loop gets compiled to this move instruction that initializes the index, that is the index of the loop, that is going to be stored in R2. And then at the bottom, we have the increment of the index, and then a conditional jump, essentially checking here whether we reach the bound or not. So here we have the access to WRAM. Notice that it's not only reading the load operation itself, but also we have to calculate the address based on what's the base address of the array and what's the index that is stored in R2, as you know. Here we have the addition operation, and here we have the store operation. Observe that for this store operation, we don't need to calculate the address, because the address is the same that we calculated before, because we are writing in the same output array, in the same position indeed. So if we execute this code, this microbenchmark on one DPU, what we obtain is something like this. The arithmetic throughput that you can see in the y-axis of these 4 plots changes with the number of tasklets that we use in the experiment. The tasklets, as you may remember, are the software threads that we use in our program. And so in this curve here, you can see how the arithmetic throughput increases as we increase the number of tasklets, and at some point it saturates and remains flat. Observe as well that here in this curve, or in these 2 curves, we have the results for addition and the results for subtraction for 32-bit integers on one DPU. These are the results for multiplication and division, and these are the results for different data types. And one key observation here is that the saturation point is always at 11 tasklets. So the maximum arithmetic throughput that we can achieve inside a DRAM processing unit is at 11 or more tasklets. And this observation is consistent across data types and across operations, as you can see in the slide. There is also something interesting here to observe is the difference in maximum throughput that we have between 32-bit integers and 64-bit integers. There is a difference of about 17% here. And we want to explain why this happens. And we can you know, imagine what are the reasons, but we are going to see it quite clearly, I believe. Because the peak throughput is achieved at 11 tasklets, we are going to assume that we are filling the whole pipeline with 11 or more tasklets. And what that means in a pipeline processor is that every cycle we retire one instruction. Every cycle, one instruction completes. So in the end, we have a throughput of one instruction per cycle. However, here we are not talking only about instructions, we are talking about operations. And remember that, for example, the addition operation entails to go to read to the WRAM, read one value, and then perform an addition, and then store back to WRAM. So the number of instructions that we are using for each operation it's going to be more than one. So the way to estimate the arithmetic throughput for a specific operation depends on the frequency of the DPU. Remember that the inverse of the frequency of the DPU is the duration of one cycle, that is the amount of time that we have to wait until the next instruction gets completed in the pipeline. And here we have the number of instructions that we need for this specific operation. And now we are going to check what our compiler produces for both the microbenchmark for 32-bit integers and the microbenchmark for 64-bit integers. And here on the right-hand side, what we see is the compiled code. This is the for loop for 32-bit integers, and this is the for loop for 64-bit integers. And if we compare both, we see that the only difference is this instruction, this add-C instruction. Remember that this ISA, the ISA of the DPU is 32-bit, is a 32-bit ISA. However, it also, the DPUs also support 64-bit operands, right? So in these instructions, we are operating on 32-bit, on elements of 32 bits, while here in this code, we want to operate on elements of 64 bits. And the way to do that, the way to support the addition for 64 bits is to have this add-C, which is an addition with carry. So in the first addition, we add the 32 bits, the least significant 32 bits of the input operands, and with the add-C, we sum the carry that comes from the previous sum plus the 32 most significant bits of the 64-bit operands. So in summary, the difference is that one operation uses 6 instructions while the other operation uses 7 instructions. And based on that, we can estimate the arithmetic throughput as 58.33 mega operations per second for the 32-bit addition and subtraction, 50 mega operations per second for the 64-bit addition and subtraction, because it's using 7 instructions. And exactly these estimates that we have here at the bottom of the slide are exactly or very, very similar to what we are measuring on the real DPU, and you can find in the upper plots. Feel free to stop me if there are any questions. Okay, another observation is the large throughput difference that we see between addition and subtraction and multiplication and division. And the key reason for that is that there is no 32-bit multiplier. Remember that since the beginning, we talked about the challenges that exist to create processing elements inside memory arrays. The DRAM technology is very different from CMOS technology, so it's pretty challenging to design a high-performance processor with DRAM technology, and this is the key reason why the DPUs don't have a 32-bit multiplier. Instead, what they are doing is emulating multiplication and division by using one instruction that performs bit shifting and addition in one cycle. Bit shifting and addition is essentially what we do ourselves when we multiply two values, two numbers with paper and pencil. The problem with this is that the multiplication and the division of 32-bit integers might take up to 32 instructions, and that's what makes that this throughput is getting reduced that much between, this large difference between addition and subtraction and multiplication and division. Another observation is the large throughput difference between integers and floating point data types. And the reason is similar to what we just saw for multiplication. The key reason for this difference in throughput is that the hardware itself, the DPUs, don't support floating point operands, and these floating point operations are emulated by the runtime library, and this is what leads to much lower throughput. So if you want to take a closer look at the microbenchmarks, or maybe even use them if you have access to an UPMEM system, you can download them from our repository. Okay, now we know what's the maximum throughput that we can achieve here in this pipeline for different types of instructions and data types. Now let's see how fast we can access data from this WRAM, either reading or writing data from this WRAM that is going to be used in this pipeline to perform the arithmetic operations. To do so, we define a new microbenchmark. In this case, our microbenchmark resembles the stream benchmark, the popular stream benchmark. We are going to present the stream benchmark in the next slide. A stream has 4 different versions: copy, add, scale, and triad. And the operations performing add, scale, and triad are addition, multiplication, and multiplication, respectively. In our experiments, we vary the number of tasklets from 1 to 16, and we show results for 1 DPU. There is one thing to mention here is that in these experiments, we are not including the accesses to MRAM in our program. The reason is that we don't want to make any noise in the measurement to the access to WRAM. And this is the, let's say, the relevant code excerpt for the different versions of the stream benchmark. In the first, so here right now, what you see is the copy stream benchmark. In copy stream benchmark, what we simply do is going over one array. In this case, buffer A and buffer B are both in WRAM. So what we do is going over buffer A element by element in WRAM, reading each element and writing it into the output array, which is buffer B. Then we have add. In add, we are using 3 arrays. 2 of the arrays are input arrays. So we read elements from these 2 arrays, we add them and store the result in the output, buffer C in this case. In a scale, what we do is reading from the input array, we multiply by a scalar, and then we store in the output array. And finally, in triad, we again have 2 input arrays, buffer A and buffer B, and we perform, as you see, 1 multiplication and 1 addition, and we store the result in buffer C. So we can count what's the amount of data movement and an amount of operations that we have in each of these versions, assuming that we are using, let's say, 64-bit integers in our experiment. Here, we would be reading 8 bytes from WRAM and writing 8 bytes to WRAM, and there are no arithmetic operations. In add, we are reading 16 bytes, 8 bytes coming from buffer A, 8 bytes coming from buffer B, and we perform 1 addition and store the result 8 bytes in buffer C. For a scale, we are reading 8 bytes, writing 8 bytes, and performing 1 multiplication. And for triad, we are reading 16 bytes, writing 8 bytes, and performing 1 multiplication and 1 addition. So here are the results. In the plot, you'll see how we present the sustained WRAM bandwidth in megabytes per second over the number of tasklets. So here, remember, we are changing the number of tasklets between 1 and 16. So these are the results for copy, these are the results for add, and these are for scale and triad. And these are the bandwidth numbers bandwidth values that we are measuring in our experiments. But we can also estimate what's the bandwidth, and these can help us understand the architecture better. We are going to assume that for our estimation of the maximum bandwidth, we are going to assume that the pipeline is full, and this happens after 11 tasklets, as you know, and actually, as you see in the plot, the sustained WRAM bandwidth in all cases saturates at 11 tasklets, as we could expect. So we assume that the pipeline is full, and bytes is the number of bytes that we read and write in each cycle, in each iteration of these microbenchmarks. This way, we can estimate the WRAM bandwidth in bytes per second as the number of bytes that we are moving times the frequency of the DPU divided by the number of instructions that we need for each of these specific operations, either copy, add, scale, and triad. So in the case of copy, we are just reading from WRAM and writing into WRAM. So it's just two instructions, a WRAM load and a WRAM store. And with these two instructions, we are moving 16 bytes. With two of these instructions, we are moving 16 bytes because the data type that we are using here in these experiments is integer 64 bytes. 64 bits. So that's each of them is 8 bytes. And if the pipeline is full, meaning we are using 11 or more tasklets, we are going to need a certain number of cycles to move a certain amount of data. So if we have 11 tasklets in one iteration of the loop, we move in total 11 times 16 bytes, and we need 22 cycles to do this, because with 11 tasklets and 2 instructions, we need to wait 22 cycles for the operation to be completed. So by using these numbers, we can estimate the WRAM bandwidth for copy as 2,800 megabytes per second at a frequency of 350 megahertz. And as you can see in the slide, you can see in the plot, it's more or less what we are measuring in our experiments. And for us, this something very similar. We can use exactly the same expression and reason in a similar way. In this case, for addition, we need 5 instructions because there are 2 loads, one at C, because we are operating on 64-bit elements, and 1 store. And remember as well that in the addition, we have 2 input arrays and 1 output array. So in every iteration of the for loop, we read 2 elements and write 1 element. And these elements are 8 bytes in size, so that means 24 bytes. If we have 11 tasklets in the pipeline, in total, we would be moving 11 times 24 bytes in 55 cycles, 11 tasklets times the number of instructions, that is 5. So in this case, our estimate is 1,680 megabytes per second. That is also very similar to what we have measured. And we can do similar calculations, similar estimations for scale and triad as well. Another interesting observation with respect to the WRAM bandwidth is that all WRAM loads and stores take 1 cycle when the DPU pipeline is full. And what that means is that the actual sustained bandwidth that we can obtain when accessing WRAM is independent of the memory access pattern. This is not a banked memory or anything like that. Every time that we go to WRAM, we are reading 8 bytes. And no matter how our accesses are, whether they are unit strided, or random, we always get 8 bytes in 1 cycle. And that's what makes that the sustained effective bandwidth of WRAM is independent of the access pattern. Same as before, our code is publicly available, and we have it's in our repository, the versions of the stream benchmark, and also the different experiment with different access patterns to WRAM. Okay, now we already understand how the instructions or how fast the instructions are executed in the pipeline, how fast we can access data from WRAM. Now it's time to check how fast we can access data from MRAM. So in summary, how fast we can move the operands between MRAM and WRAM using this DMA engine. So our goal is to measure the MRAM bandwidth for different access patterns. We create also several microbenchmarks here. With the first one, what we are going to do is just measuring what's the latency of a single DMA transfer for different transfer sizes. The UPMEM SDK provides 2 instructions to move data between MRAM and WRAM to handle these DMA transfers. And these instructions are MRAM read and MRAM write. So with an MRAM read, we are reading from MRAM and writing into WRAM. With an MRAM write is in the opposite direction. We are also going to use the stream benchmark here. Same as before, you're already familiar with how the for loop of a stream benchmark looks. We are going to anyway see the corresponding versions as well in one slide. We have also created microbenchmarks for strided access patterns, and we actually have 2 different ways of doing strided access patterns. For everyone to be on the same page, just let me tell you that a strided access pattern is when consecutive accesses to memory are at a certain distance, and this distance is fixed. The access can be a stride equal 1. In that case, we talk about unit stride, or a stream, accessing a streaming, or the stride might be more than 1, might be 2, might be 4, might be 5, etc. We have experimented with different strides as well. And then we create as well one microbenchmark to measure what's the bandwidth for random access patterns, and this microbenchmark is based on the popular GAPS benchmark. In this case, we include the accesses to MRAM, makes sense, as opposed to what we did for WRAM, but here it makes sense because that's actually what we want to measure, the bandwidth, the latency and bandwidth to MRAM. Okay, let's start with the latency. So here you have 2 plots. One is for MRAM read, the other one is for MRAM write. On the left y-axis, we have the bandwidth in megabytes per second. On the right y-axis of each plot, we have the latency in cycles. And here at the bottom, because we are measuring the latency for a single MRAM read or MRAM write, what we have is the data transfer size. So we are using transfers from 8 to 2048 bytes, as you can see in the slide. And these are the results. The lighter blue is the latency, the darker blue is the bandwidth. The way that we obtain the bandwidth is from the latency measurement that we do. So we are measuring the latency in cycles, and then using this expression here, we obtain the bandwidth. Notice that in this expression, we have the size of the transfer, either 8, 16, or 2048 bytes, and we multiply that by the frequency because the MRAM latency is measured in cycles. And one thing that we observe as well is that we can model the MRAM latency that we measure. We can model it with a linear expression that looks like this. It's alpha plus beta times size. And notice that our model or linear expression matches pretty well what are our measurements for both MRAM read and MRAM write. And actually, according to our measurements and according to this expression, beta equals 0.5 cycles per byte. And this beta is essentially the inverse of the bandwidth that we can obtain from MRAM, as we will see. And actually, by using this beta, we can estimate the theoretical maximum MRAM bandwidth in 700 megabytes per second in a single DPU at a frequency of 350 megahertz. So one key observation here is that the latency of the MRAM accesses increases linearly with the transfer size. As you see, the larger the size, the larger is going to be this MRAM latency, and the dependence is linear, as you see from the expression. And also, and according to our measurements, the maximum theoretical MRAM bandwidth is 2 bytes per cycle, which means up to 700 megabytes per second at a frequency of 350 megahertz. Okay, another observation is that MRAM read and MRAM write are symmetric. As you see, both curves here, bandwidth and latency, are very similar for both MRAM read and MRAM write. The other observation here is that it's better to use larger transfers, right? So if you are going to access data that you bring from the WRAM, from the MRAM to the WRAM, it's better to use larger data transfers, essentially because we are exploiting higher bandwidth. So as you see, for 1024 or 2048, we are in the maximum, and actually here the bandwidth is already pretty flat, and it's significantly higher than for 8 or 16 bytes. Another observation here is that the MRAM latency is pretty flat between 8 and 128 bytes. And the reason is that for small transfers, the fixed cost alpha of the linear expression that we presented before dominates the variable cost beta time size. So one programming recommendation is kind of ninja programming recommendation, because you really have to know what you're doing. But the programming recommendation here is that because the latency, the difference in latency between bringing 8 bytes or bringing 128 bytes to the WRAM is so small, it might make sense to bring 128 bytes, because maybe after using the first 8 bytes, we can make use of the remaining 120 bytes that are already in WRAM. And to do so, the only thing that we're going to need to do in our code is checking if something is in WRAM, one particular address has been brought to WRAM before going to MRAM to fetch new data. Okay, another observation, interesting one, is that the 2048 byte transfers are only 4% faster than the 1024 byte transfers. As you see, the bandwidth is pretty flat for these two transfer sizes. However, there is one consideration here. In principle, you could say, okay, if I want to maximize my bandwidth and I know that I'm going to use all the data that I'm bringing to WRAM, let's use the larger transfer that we can use, in this case, 2048. But that has also its own dark side, its own drawback. The fact that I'm bringing a larger chunk from MRAM to WRAM means that I need to allocate data space in WRAM. And the total amount of WRAM is relatively small. It's only 64 kilobytes. And these 64 kilobytes are shared by all tasklets that we are running on the same DPU. So if we are using 16 tasklets, it's only 2 kilobytes per tasklets, right? Out of the 64 kilobytes. So what this means is that we may end up, depending on how much data or how much space we need to allocate in WRAM for each tasklet, it may end up happening that we need to reduce the number of tasklets that we use, right? Observe the example that I just gave you. You have 64 kilobytes in total. If you are using 16 tasklets, this means 4 kilobytes per tasklet. If your transfers are, you use transfer of 2048 bytes, that means that you can only have 2 arrays of 2048. So if you eventually need to hold data from a third array, you couldn't fit in the amount of space that you have. And in that case, you would need to reduce the number of tasklets that you use in the program. If you don't want that to happen, what you can do is using smaller transfers. 1024 byte transfers would allow you to have 4 arrays of 1024 byte allocated in WRAM per tasklet. So this might be important in terms of the occupancy of the DPU or the number of tasklets sorry, that we are running on the system. Okay, let's go to the next experiment here. This is the stream benchmark. Let's measure directly what's the bandwidth that we can obtain from the MRAM. You are already familiar with this copy stream benchmark. It's just reading from WRAM and writing into WRAM in a different array. But here we are also including the accesses to MRAM. So we have to have this MRAM read that brings something from MRAM into the buffer A, and after moving data in WRAM, we have to write back the from buffer B in WRAM to the corresponding memory address in MRAM. We have another version of the stream benchmark, and we create this version because if you really want to do what the original copy benchmark does, is just moving the contents of one array to another array in MRAM, you don't really need to do it using WRAM, right? You can simply, or let's say streaming over all the elements in WRAM, you can simply copy from MRAM to buffer A, and then copy from buffer A to the destination address that is whatever address B. There is a small typo here. This should also be buffer A because we are bringing from MRAM to buffer A and then from buffer A back to MRAM. And let's observe what are the results for the stream benchmark. First one is copy DMA, this version that doesn't go through WRAM. What we observe here, first observation here, is that the sustained bandwidth of copy DMA is close to the theoretical maximum of 700 megabytes per second that we estimated before. So for a large system, and the larger UPMEM-based PIM system that we have tested had 2,556 DPUs, the aggregated bandwidth is around 1.6 terabytes per second, which is pretty high. One observation as well here is that for the copy DMA engine, the copy DMA microbenchmark, the arithmetic, the bandwidth saturates at 2 tasklets. The reason for that is simply that using more than 1 tasklet makes sure that there is always a DMA request waiting in the queue, and this keeps the DMA engine busy. But there is not really parallelism in the accesses from different tasklets, because there is a single DMA engine, and this DMA engine can only sustain 1 access at a time, 1 transfer at a time. Now we can take a look at the bandwidth for copy and add, and what we observe here is that the bandwidth for copy and add saturates at 4 and 6 tasklets respectively. However, for scale and triad, the saturation point is at 11 tasklets. The reason for this is that as we start increasing the number of tasklets from 1 to 4 or to 6, what we are doing is also increasing the total latency of the data transfers of the MRAM WRAM and WRAM MRAM transfers that we are requesting to the DMA engine, because these transfers are sequential, because there is a single DMA engine and it can only sustain a single transfer at a time. Every time that we start executing a new tasklet, we are increasing the total latency of access to MRAM, right? And what happens for these 2 particular benchmarks, copy and add, is that after 4 and 6 tasklets respectively, this latency latency MRAM accesses becomes longer than the pipeline latency, that the execution of instructions in the pipeline for these particular microbenchmarks. However, for scale and triad, regardless of the number of tasklets that we are using, the latency of the pipeline is always larger, and because that happens, these two microbenchmarks saturate at 11 tasklets because the pipeline saturates at 11 tasklets, as you already know. So important observations here are, if one particular workload saturates with less than 11 tasklets, it's likely that the access latency to the MRAM bank is hiding the execution of instructions in the pipeline. And we call this a memory-bound workload in this architecture. However, if it happens the other way around, if the throughput saturates, the performance saturates at 11 tasklets, this means that the pipeline latency hides the latency of accesses to MRAM, and this is what we call a compute-bound workload on this architecture. Okay, next experiment is for strided access pattern and for the random access pattern. And as I said before, we have two different ways of doing the strided access patterns. For the random access pattern, we only use one of these two ways. These two ways are coarse-grained strided access and fine-grained strided access. In the coarse-grained strided access, what we essentially do is bringing a whole chunk of data from MRAM to the WRAM, and then we perform the accesses in WRAM, and we perform these accesses in a strided manner with a certain stride. And this is what you can see here. Instead of increasing this index I by 1 in every iteration, we are doing it by a stride. So if this says, for example, 2, we could be only accessing the even numbered elements of buffer A and buffer B. So this is the, in this case, we are first of all performing this MRAM read operation for both input arrays A and B. Then we stride, so we perform the strided accesses in WRAM, and finally we write from WRAM to the MRAM, the say output of the accesses. In the case of the fine-grained strided, and also in the case of the random accesses, we don't use or we don't perform the accesses inside WRAM. We simply go to MRAM to fetch one element, to fetch the element that we need. In this case, and that's the reason why we are only transferring in both this MRAM read and MRAM write, we are only transferring 64-bit unsigned int. It's just one single element of the input arrays. Okay. So let's take a look at the results. Again, we have in the y-axis, we have the sustained MRAM bandwidth, and the left-hand side, we have the results for coarse-grained strided accesses. In the right-hand side, we have the results for fine-grained strided and random accesses. And these are the results for different number of tasklets. Each curve corresponds to a different number of tasklets. And at the bottom, in the x-axis, what we have is the stride that we are using in the strided accesses. And also here, this last column here, the rightmost one corresponds to the results of the GAPS benchmark, the random access patterns. So first observation here is that there is a large difference in the sustained maximum and the maximum sustained bandwidth between the coarse-grained and the fine-grained DMA. Notice that the maximum bandwidth for the coarse-grained DMA access, it's for stride 1, which means that we are using all the elements that we are reading from MRAM and placing them into WRAM. And this large difference in the bandwidth, in the sustained bandwidth, is due to the transfers that we are using. Either 1024 byte transfers for the coarse-grained strided access, or only 8 byte transfers for the fine-grained DMA access. And in random access, as you see, we achieve very similar maximum sustained bandwidth because we are using the same type of transfers. Another observation is that the sustained MRAM bandwidth of the coarse-grained DMA accesses decreases as the stride increases. The reason for that is that in reality, we are bringing a whole chunk, but we are not using all the elements that we are bringing when we increase the stride. For 2, we could be only using half of the elements that we moved from MRAM to WRAM. With a stride of 4 means that we are only using 1/4 of the transferred data. So essentially what we are doing is dividing the effective bandwidth because we are not utilizing all the elements or the data that we are bringing from WRAM to MRAM, and that's what makes that the effective bandwidth decreases that much. Another observation is that after 16 tasklets, after a stride of 16, the coarse grain strided access provides lower bandwidth than the fine grain strided access. As you see, this 77 corresponds to a stride of 8 after 16. So for a stride of 16, it's essentially half of these 77, and that's already smaller than this 72.58 that you see here on the right. So yeah, with a stride of 16, we are only using 1/16 of the maximum bandwidth, and that's what makes that it's, let's say, more efficient to use the fine grain accesses. So this is also a programming recommendation, depending on how are we going to access memory, depending on what's the stride. If we are using strided accesses in our workloads, we are going to prefer either a coarse grain approach or fine grain approach, yeah, depending on the stride. And these codes are also available in our repository. And the last set of experimental results that I want to show you are connecting the whole thing. First of all, we focus on measuring the arithmetic throughput. Then we have measured what's the bandwidth to WRAM, to MRAM. Now we are going to compare the arithmetic throughput depending on the operational intensity to the latency of access to the MRAM and the bandwidth of access to the MRAM. And to do so, we create one microbenchmark that is going to characterize the memory bound regions and compute bound regions for different data types and operations. This microbenchmark loads one chunk of an array in MRAM into WRAM, then performs a variable number of operations on the data of this array, and then writes back to MRAM. The experiment, as you will see, is inspired by the Roofline model, a methodology that presents the performance of a program based on its arithmetic intensity or operational intensity. In our particular experiment, we define the operational intensity as the number of arithmetic operations performed per byte accessed from MRAM. So we measured this operational intensity in operations per byte. And in this particular experiment, we are varying, that we are changing the number of operations that we perform on the data. So we are changing the operational intensity in different experiments. However, the size of the transfers is always the same. The size of the MRAM WRAM transfers is always the same. So the MRAM access latency is fixed. And this is the microbenchmark. I don't want to spend much time here, but here you can see the transfer from MRAM to WRAM, the MRAM read. Here we have the operation itself, in this case, one addition, and this is the MRAM write. And as you see, we have a couple of for loops. These for loops are, to let's say, control what's the operational intensity, how many operations we perform on the specific, the values that we have in WRAM. There is some stride here because for very low operational intensity, we are not even going to operate on all the elements of the array. So we would be jumping. For higher operational intensity, the stride is equal to 1. And what we do is repeating many times on each element of buffer A. And here you can see some results. These are for addition and multiplication of 32-bit integers and floating point, single precision floating point. The plots present the arithmetic throughput in the y-axis over the operational intensity from very, very low values. This could be just one operation every 2048 bytes. This would be 8 operations per byte. So from very, very low to relatively high operational intensity in all experiments. And here you see the results, as I said, for 32-bit integer multiplication and addition, for multiplication and addition of single precision floating point. One first observation here is that the trends are pretty similar. We see some part of the plots where we see how the arithmetic throughput increases with the operational intensity, and at some point this arithmetic throughput saturates and it remains flat after that. And we can take a closer look, more detailed look at one of the plots, in particular this one, addition of 32-bit integers. This result here is the arithmetic throughput for a single tasklet and for this low arithmetic intensity of 1/2048. This is the arithmetic throughput for 2 tasklets. We see that it increases slightly, but after that, the arithmetic throughput remains flat for higher number of tasklets. Why is that? The throughput saturates at less than 11 tasklets. And remember one of the observations from previous slides. If the performance of a program saturates with less than 11 tasklets, it's probably because the workload or the program is behaving as a memory bound on this architecture. And as you see, this trend more or less remains until higher values of the operational intensity. So even for 1/64, we still, the throughput still saturates with only 2 tasklets. After that, for 1/32, it saturates in 3 tasklets. So we need more tasklets to saturate the throughput, which means that we are getting closer to the compute bound area of the roofline. And the trend continues, but also we need more tasklets to achieve the higher throughput. And at some point, we see how the throughput starts saturating at 11 tasklets, and it remains constant up to 16 tasklets, which is the maximum number of tasklets that we have used in our experiments. And these are the results for higher operational intensity. So here we can differentiate between the memory bound region, where the arithmetic throughput increases with the operational intensity, and also the such saturation of the arithmetic throughput happens with less than 11 tasklets, and the compute bound region, where the arithmetic throughput is flat at its maximum and the throughput saturates at 11 tasklets. And the transition between the memory bound region and the compute bound region is what we call the throughput saturation point, which you can see is very low. Even in this micro benchmark is as low as 1/4, one operation every 4 bytes. That essentially is one integer addition every 32-bit element that we fetch from memory. And the throughput saturation point is actually very low in all cases. It's even lower for multiplication or for floating point operands. And the fact that it's so low, this saturation point is so low, means that we can expect that most of real-world workloads are going to be in the compute bound area of the processor. So we can say that this is a compute bound processor. Okay, and here you can access the code as well from our repository. So in order to summarize, I would say that one key takeaway of this lecture is this differentiation between memory bound region and compute bound region. Depending on what's the operational intensity of our workload, we have observed this by using a very simple but very powerful micro benchmark. We notice that the throughput saturation point is very low in all cases, even for integer additions is as low as 1/4. So key takeaway here is that the UPMEM PIM architecture is fundamentally a compute-bound processor. So we expect that most real-world workloads will be compute-bound in this architecture, but of course, we should also expect that the most suitable workloads are memory-bound in conventional architectures. We will continue talking about the UPMEM PIM system in later lectures, probably not the next one. We are going to talk about how to program this UPMEM PIM system in a later lecture, and we will see more benchmarking that we did with real-world compute patterns. Yeah, if you cannot wait, you can go to our paper and read it, or watch some of the previous lectures or talks that we have delivered on the topic. And in later lectures, we will continue talking about real-world processing in memory architectures. Next lecture, we will talk about the Samsung HBM PIM architecture, and we will probably show as well some details about the SK Hynix architecture. And as I said before, in later lectures, we will continue talking about the PIMC, the UPMEM PIM system, working on, how to program this system, and we will talk as well about how characterized workloads to identify PIM suitability. So this is all for today. I don't have any more slides. Feel free to ask any questions now, or you can also contact me later, and I will try to clarify any questions you may have. Okay, yeah, thank you very much, guys. I guess there are no questions, so we are done for today. I hope to see you all in